So today's lecture is going to be about instruction scheduling. So last time, what was the topic of last lecture?
Instruction selection.
Register allocation? Okay. So what's register allocation? How would you describe it? Yes, sir.
Mapping virtual registers to physical registers.
Yeah, exactly. So it's mapping virtual registers into physical registers. And what's a virtual register? What's a virtual register? Yes?
Part of the abstract assembly that's generated by the backend.
Okay, yes, it's part of the abstract assembly. But what does a virtual register correspond to? What does it represent? Yes?
It makes the assumption that you have an infinite amount of registers.
Yes, exactly. When you are using virtual registers, you are making the assumption that you have an infinite number of registers on the machine. The compiler assumes that there is an infinite number of registers on the machine until it gets to register allocation. So in register allocation, now things get real. Now we're going to map these virtual registers into physical registers. So a virtual register could be one of two different things. So what does a virtual register correspond to in the source program? Yes?
A variable.
Yeah, so it corresponds to a variable. But a virtual register could be something else. It doesn't have to be a program variable. It could be
temporary value.
a temporary or an intermediate, a temporary variable that holds some intermediate result. Okay, so that was the register allocation stuff. Now today we will be discussing instruction scheduling. Instruction scheduling was briefly described in the previous lectures. Today we're going to study it in detail. So let's look at our the same example. X equals A times B plus C divided by D. Let's look at this example. The abstract syntax tree for this is going to be, multiplying A and B and dividing C by D and then adding the results and then assigning to X. Okay. So now let's write some assembly code, some virtual assembly for this. So let's stick to the code that we wrote last time. So we have load A into register R1. By the way, last time we pointed out that this load A is the shorthand for a load instruction that takes a register and an immediate. So this A here represents what in the assembly? So in an actual assembly, this A will be an offset. So it will be just a number, an integer, an offset relative to the activation record pointer. So loading A into R1, loading B into R2, then multiplying R1 and R2 and putting the result in R3, then loading C into register R1, loading D into register R4, R5, and then dividing what by what?
R4, R5.
R4 by R5 and putting the result in R6, then adding R3 and R6, putting the result in R7, then storing R7 into X. Now, the point is that when we have code like this, some of these instructions, like the load instructions, some of them have long latencies. So it takes a certain number of cycles for the result to become available. So if we assume, let's assume that the following latencies. Let's assume that for the load, we have a latency of 3 cycles. For a multiply, 2 cycles. For a divide, 5 cycles. And for a store, 2 cycles. And for the add, 1 cycle. Usually we mention the ones that are greater than 1, the instructions that have a latency greater than 1, and everything else, by default has a latency of 1. So, but in this case we only have the add, so we just mention it explicitly. Okay, so with these latencies, let's try to count the number of cycles that this sequence of code is going to take. So let's do the let's try to count the cycles. And so start and end. So assuming that we start in cycle 1, this load will take 3 cycles. So it's going to start in cycle 1 and end in cycle 3. Okay. Now, modern processors offer you the option of executing instructions in parallel. So what's the architectural feature that allows you to start a new instruction in each cycle, even if some instructions have not completed?
Pipelining.
Pipelining, exactly. So with pipelining, you may start a new instruction even if some instructions have not completed yet. And in this case, let's assume that we can start a new instruction, one new instruction in each cycle. So this is a single issue machine. We are assuming a single issue machine where in each cycle we can start a new instruction, but assuming that this instruction is what? In every cycle we can start a new instruction, assuming what?
It's ready.
The instruction is independent of the previous instruction.
Exactly. That's the point. So as long as we have an independent instruction, an instruction that does not depend on the instruction that is currently executing in the pipeline, we can start a new instruction. So here, with this load, is it dependent or independent? It's independent. It doesn't depend on this. So we can start it. This is, sorry, start. So we can start it in cycle 2 because it's independent, and it's going to finish in cycle 4. Now this multiply, is it dependent or independent?
Dependent.
It's dependent. In fact, it depends on both. And since we are talking about dependence, compilers construct what we call the dependence graph for this. So if this is, let's number the instructions. If this is instruction 1, instruction 2, 3, 4, 5, 6, 7, 8, then the compiler would construct a data dependence graph, which is very much, for this simple example, it's an inverted abstract syntax tree, basically. So it's going to be 1 and 2. 1 and 2 are independent, and 3 depends on both 1 and 2. So in this case, 3 depends on 1 and 2 because it uses the results of 1 and 2. So this is our data dependence graph. Okay, now the multiply is dependent on both of them, so it can't start any earlier than cycle 5. So cycle 5 is the earliest cycle for the multiply to start, because this completes in cycle 4. The result of this will be available in register 2 in cycle 5. This is our assumption. Now this is going to take cycles 5 and 6. Now the load, is it dependent or independent? Does it depend on the result of the multiply? No, it's not consuming, it's not using the result of the multiply, so it's independent. So we can just start it in cycle 6. We don't have to wait for the result of the multiply. Okay, so this is going to start in cycle 6. So instruction number 4 is independent. And the same applies to instruction number 5. So this is going to be 6 to 8, 6, 7, 8. And this is going to be what? So should this be 9 or 7?
7.
Why 7?
It doesn't.
Yeah, it doesn't depend on the previous instruction. So it can start in 7. You can start a new instruction as long as it doesn't depend on previous instructions. So this is going to be 7 to 9. OK? And now, the divide, is it dependent or independent? It's dependent. So we have 4 and 5. They are both independent. And they feed 6. So 6 is fed by 4 and 5. It uses the results of 4 and 5. This is our data dependence graph, which is in this example, it's just an inverted abstract syntax tree. But generally speaking, it's not the case. You know, the dependence graph is not, it's more complex than that. But for this simple example, it is. So the divide is dependent. So what should be the starting cycle for the divide? 10. Then the divide is 5. So it's going to be 10 to 14. OK? 10, 11, 12, 13, 14. Now, the add, is it dependent or independent?
Dependent.
It's dependent on the divide. It's dependent on this and this, actually. This dependence is not a big deal because the result is already available in starting cycle 7. But this is the dependence that is going to cause a delay. So we can't start this add any earlier than cycle 15 because it's dependent. And so our dependence graph here, 7 is dependent on 3 and 6. And 8 is dependent on 7. So this data dependence graph is very intuitive, right? Now, the result is going to be available in 16. And 16 and 17, we will finish the store. So we needed 17 cycles. Now, this is just this is just an estimate, by the way. This is just an estimate that the compiler is making. The compiler is making this estimate based on the latencies, based on instruction latencies, and based on a certain processor model. So it depends on this whole thing depends on these calculations depend on the processor model. But one of the assumptions that we are making here in our calculations, are we here assuming that the loads are going to hit or miss in the cache? Hit. So we're assuming that each load takes a couple of cycles or 3 cycles. This is assuming a cache hit. Because with a cache miss, bringing something from main memory takes how many cycles?
Forever.
No, it's hundreds. So on a modern processor, it's going to take hundreds of cycles. So it's 2 orders of magnitude more than bringing something from the cache. So, by the way, everything that the compiler does, it does not necessarily have to match the reality when you run the program. So the compiler makes certain calculations and certain estimates, but these estimates are not going to be 100% true. The compiler can make guesses and estimates in terms of performance, but in terms of correctness, the compiler cannot guess. So the compiler must be correct, must generate correct code, but in terms of performance, it can make some guesses and estimates. So in this case, for example, one of the implied implicit estimates is that these loads are hitting in the cache. In fact, if they miss, then this whole calculation will not make sense because we need hundreds of cycles for a cache missing memory operation. Yes?
Can the compiler know if it loaded in that memory location before, so it'd be in the cache?
Okay, so this is a good question. If the compiler has loaded this before, then we can assume it's in the cache. Can we always assume that something that has been loaded before is in the cache?
No, it might.
No, because it may have gotten knocked out of the cache by something else. And in fact, if you are at a certain point in a program, so this is your program, and you are here in the program, you have a load somewhere here in the program. In general, your program will have lots of conditionals, lots of if-else, which means that there are many, many paths that can get you from the starting point, the entry point, to this point. So there are multiple paths. Because on the way, there are lots of if-else, lots of conditionals. Now, not knowing the path means you don't know what's in the cache. Because what's in the cache, the state of the machine is dependent on the path that took you from the entry point to this load. Okay, so for example, you could have an if statement, if execute a huge piece of code. So we don't know if that huge piece of code got executed or not, because in general, the compiler doesn't know if an if statement evaluates to true or false. Remember that we are doing all of this at compile time. Keep in mind that we are not running this program. We are compiling. We're just translating. We're translating high-level machine code, high-level source code into machine code. That's all what we are doing. We're not running the program. Yes, yeah. So you can model the processor, like I said. You can always model the processor, but this model will never compile time information will never be 100%, will never match runtime information 100%. Okay, yes?
Even if you did have the instruction immediately prior pulling something in from memory, you can't really guarantee it's in the cache because you could have task switching going on. So if another process gets loaded, that could kick your stuff out of the cache.
Yes, there are so many factors that you don't know. So the compiler can only guess, and this guess may or may not be right. But remember that the compiler is allowed to guess when it comes to performance. It's not allowed to guess when it comes to correctness. The code has to be correct. And the performance, we want it to be as good as possible. Okay, so now this is our estimate based on this simple machine model, our estimate of the number of cycles. Now a compiler would do instruction scheduling. By the way, we haven't yet said what an instruction scheduler would do. An instruction scheduler would look at this, and it would try to reorder these instructions to minimize the number of cycles. So an instruction scheduler in this case may notice that these loads have long latencies, and these loads are independent. So I can execute all the loads in the very beginning, and then do everything else afterwards. So an instruction scheduler may do this. Load A into R1, load B into R2, load C into R4. So we are just looking at these instructions and reordering them. So we are reordering these instructions in an attempt to minimize the number of cycles needed to execute this sequence of code. So loading C into R4. So basically, we put instruction 4 before instruction 3. That's what we did. Loading D into R5. Then we multiply R1.
Wouldn't it be faster to run the division first? Division takes longer.
Okay. Well, that's a good point. Yes. So the division takes longer than the multiply. But the question is, will the results of the division be available or not? So, well, in fact, what you are suggesting is that the division is slower. So we can load C and D before loading A and B, because C and D are the operands that the division needs. And we can do this and do that before the division, then do the division. Yes, so we can do that. So here we are not, by the way, we're not trying to construct the optimal schedule, because as we will see, there is no known algorithm that can always find the optimal schedule. But what you are suggesting is good. Yes. Now let's stick to this. Just putting the loads in the beginning, and then doing the multiply, then doing the divide, which is R4 and R5. So we put this loading into R5, R1 and R2, we put this into R3, and R4 and R5, we put this into R6, and we add what? R3 and R6, and put this in R7, then store R7 into X. Okay, so now let's count the cycles. So this is start and this is end. So this is going to start in 1 and end in 3. And this, is it dependent or independent? Independent. So it's going to start in 2 and end in 4. And this, also independent. So it's going to start in 3 and end in 5. This is also independent. So it's going to start in 4 and end in 6. Now the multiply is dependent. What is it dependent on? It's dependent on R1 and R2. So R2, the result in R2 will be available in cycle 5. So we can do cycle 5 here. Okay, because R2 is this. So R2 will be available in cycle 5. So the multiply can go ahead in cycle 5, 5 and 6. Then the divide is dependent on R4 and R5. So the latest result that it needs is in R5, and this will be available in cycle 7, right? Yeah. So the divide is going to start in cycle 7 because it needs the R5. So 7, and it's going to be 6 plus 5 is 11. So it's going to end in 11. Now the add is dependent on the divide. So it will have to wait until cycle 12. And 12 to 12. And this is 13 to 14. So in this case, 14 cycles. So in theory here, the compiler has reduced the number of cycles needed to execute this from 17 to 14. And it did this by basically hiding the latencies of the loads, or hiding the latencies of these independent instructions by placing some independent instructions. It placed independent instructions between this load and the consumer of the load, which is the multiply. So the multiply consumes the result of the load. The load has a long latency. So in this long latency, we put some independent instructions. This is the point. By doing this, we are doing more instruction level parallelism. So we are doing instruction level parallelism. We are doing more instructions in parallel. Why? Because here, basically, we are doing all of these loads, all of these 4 loads, they're executing in parallel. Okay? They're all in the machine, and they're executing in parallel. Here, we are only doing 2 loads in parallel. Okay? So in this case, this is more instruction level parallelism. So this has more ILP. More instructions executing in parallel. Now there is a cost for everything. So the cost here is using more registers. This schedule here needs more registers than this schedule. So let's analyze the registers that are live for each one of these two schedules. So here, let's look at okay. Okay. So this is live registers. So now live registers here. After executing this instruction, R1 will be live. So it's defined here and it's used here. After executing this, live registers are going to be R1 and R2. Both R1 and R2 at this point are live because they have been defined and they will be used later. And later is here. This is the last use. Now at this point, after the execution of instruction 3, which registers will be live? R3 only. What happened to R1 and R2? They are no longer live because they are not used below instruction 3. So instruction 3 is the last use of R1 and R2. So if we had something that uses R1 here, then R1 would have continued to be live. But since there is no use for it below this point, this is the end of the live range. So R1 and R2 are not live. Only R3 is live here. And with this instruction, what will be live? R3 and R4. And with this, R3, R4, and R5. And with the divide, which instructions will be live?
R3 and R6.
Yes, R3 and R6. Why?
Because we still need R3 and the next instruction.
Yeah, you still need R3. You still need it here. So R3 is live. But R4 and R5 will not be live after this instruction. They are not used below. Okay, so only R3 and R6 are live. And here, R3 and R6 are used. So they are no longer live. Only R7 is live. And here, nothing is live. Okay. Now, if we look at the register usage for the other schedule, live registers. So for this, the live registers are R1. Now R1 and R2. Here, yeah, R1, R2, R4. And here, R1, R2, R4, and R5. Here, we are using R1 and R2. And this is the last use of them. So R1 and R2 are no longer live. So we are left with R4, R5, and R3 has also become live. Here, we're using R4 and R5. So R4 and R5 are no longer live. But now we have R3 and R6. And here we are using R3 and R6, and only R7 is live. And here we have none. Now the question is, what's the minimum number of physical registers that you need here? And what's the minimum number of physical registers that you need? So this is schedule 1. And this is schedule 2. So here, this is your peak. This is the maximum. So at this point, you have 3 registers live that are live. So this is your maximum or your peak register pressure. At this point, you need at least 3 registers, because at this point, you have 3 values that are live. So you need 3 physical registers here, at least. So this is your peak register pressure. While here, what's our peak? 4. So our peak is here. So this is the peak register pressure. So the difference between this schedule is, schedule 1 is 17 cycles, but needs 3 physical registers, 17 cycles, and it needs 3 physical registers. Schedule number 2 is 14 cycles and needs 4 registers. So basically, reducing the number of cycles required more registers. Nothing comes for free. And this is very intuitive, because here you are doing more things in parallel. You are doing 4 instructions in parallel. You need 4 registers. You need containers for these to store the results of these. So it's just like cooking, for example. If you are trying to cook and you are trying to cook in parallel, and if you want to cook meat, rice, and vegetables at the same time, then you need at least 3 containers, right? You cannot do it with 2 containers. If you have 2 containers, you cannot cook 3 things at the same time. And what is happening here, these 4 instructions are cooking. So this is instruction level parallelism. So they're cooking at the same time, so you need containers. For more parallelism, you need more containers. So that's why this is intuitive. Now, what does the compiler do? So should the compiler try to minimize the number of cycles and use more registers, or should it minimize the number of registers and minimize the number of registers and use more cycles, or minimize the number of cycles and use more registers? Yeah.
Does that depend on the architecture of the processor?
Yes. Yeah, exactly. So it depends on the architecture, on the target processor. It depends on how many physical registers you have on the target processor that you are trying to generate code for. So, in this case, for example, if you have 4 physical registers available, then you can go ahead and do this more instruction level parallelism and minimize the number of cycles, and that will work out well. But in general, this is a hard problem to solve. In fact, instruction scheduling, any realistic formulation of instruction scheduling is NP-complete. Okay? So, in fact, only minimizing one of these 2 objectives, the number of cycles or the number of registers, is in general NP-complete. So, even if our only objective is finding the ordering that will minimize the number of cycles, even then, with long latency instructions, that's an NP-complete problem. And even if our sole objective is minimizing the number of registers, that's an NP-complete problem. So what's an NP-complete problem? How would you define NP-complete? Yes?
It's equivalent to, it's a class of problems that are all equivalent to each other that have no polynomial time solution.
Yes. Yeah. So there is no polynomial time solution, which means there is no polynomial time algorithm that can always compute the optimal solution to this problem. There is no polynomial time algorithm. Not having a polynomial time algorithm means that the algorithms that you have are exponential, super polynomials, so they're exponential or factorial. And exponential and factorial algorithms take a long time. For practical purposes, if you have, for example, a problem with n equals 100, So in our case, n is the number of instructions. So 2 to the power 100. So this is a huge number. So if you do the math for this you will get millions of billions of years. So it means that if you want to run an algorithm, an exponential algorithm that will be trying to find the best ordering in this case, it's going to take billions of years in the worst case. Okay? So compilers, that's why compilers don't solve this problem exactly. So they use certain heuristics, and these heuristics hopefully work well in most cases, but not in all cases. So a good heuristic is a heuristic, an algorithm that is not guaranteed to give you the optimal solution, but it gives you something close to the optimal solution in most cases. This means that there may be some extreme cases where this algorithm will not give you the best results. Now, the question is, if you are designing an algorithm for instruction scheduling, should you focus on minimizing the number of cycles or focus on minimizing the number of registers? Now, again, this depends on the target architecture. And in fact, if you are generating this code for an out-of-order processor, what does an out-of-order processor do in this case? And why is knowing whether the processor is out of order or in order, why does it matter?
Because the out-of-order processor will do what the Schedule 2 does automatically.
Yeah, exactly. So hopefully, the out-of-order processor is going to do this at runtime. Well, but it's not going to do a perfect job. It's going to do a good job. Nothing is perfect, by the way. The processor is not perfect, and the compiler is not perfect. So nothing in the system is perfect. But an out-of-order processor will be trying to do something like this, hiding the latencies. And in fact, it will be using internal registers that are not visible to the programmer to achieve more parallelism. So if you have an out-of-order processor, then you better focus on minimizing the number of registers. You better focus on minimizing the number of registers because, as we have seen in the register allocation lecture, last lecture, if you need more registers than what the machine has, the register allocator is going to generate what?
Stores and reloads.
Stores and reloads. And we call those what? Spill code. So it's going to spill. It's going to generate spill code. So if your processor has out-of-order execution and it has a good out-of-order execution engine, you better focus on minimizing the number of registers, because minimizing the number of registers needed is going to cause the register allocator to generate fewer spills, fewer loads and stores. So that's much more important than minimizing the number of cycles, because the processor is going to try to minimize the number of cycles. Now, will the processor do a perfect job at this? The processor has limitations. So in terms of scheduling to minimize the number of cycles. So can you think of a limitation of the processor?
Well, the main one is once it gets done with the loads, it's dependent on the result. So multiply and divide before it can go to the add.
Well, in this case, yeah. So it's well, in fact, we'll assume that the processor will have. So if you present this to a processor, it's gonna do the load. Then it will do the load. Then this multiply, is dependent on the load. But because the multiply is dependent on the load, the processor is not gonna stop. So it's gonna go and that's what out-of-order execution means. So it's gonna start the load while this multiply is waiting for its results. So at runtime, the processor will be starting the load before the multiply completes. So it's going to start the multiply. It's going to issue the multiply But the multiply will not, before the multiply completes, it's going to start the load trying to do more parallelism. But what are the limitations of the processor? Why is the processor limited? I mean, why can't the processor do a perfect job? Can you think of a limitation? Yes?
It can only look so far ahead.
Exactly. Yeah, the scope. It can only look so far. So this is going to be in the reorder buffer. So there is a buffer. You know, it can look only at a limited scope, what can fit in a buffer, in a certain buffer. So it's not going to look, you know, at the entire program. And that reorder buffer will have tens of instructions in it, only tens of instructions, maybe 64, 96. I don't know, maybe they have gotten bigger now, maybe 128 or something, but that's about, you know, the range for a reorder buffer. So the processor can only look at this limited scope, which is the size of the reorder buffer, while the compiler can look at a bigger piece of code, even though there are limitations on the compiler side too. So the compiler, there is no compiler that schedules a whole program at once, because scheduling a whole program at once is just too complicated. You don't expect a compiler to schedule, you know, a 1,000,000-line program and, you know, move the, you know, line number 1 and put it at the end. So it's not going to do this at the scope of the whole program. It's going to divide the program into pieces, into scheduling regions. And these scheduling regions are limited in size too, but they can be bigger than the reorder buffer on the hardware. So the size of the scheduling region, you know, the compiler may look at hundreds of instructions and sometimes at thousands of instructions at the same time. So it can do thousands sometimes. But not, what about what?
Sorry to interrupt you, but I was thinking, what about the, a lot of the processors today have jump prediction. So how does that factor into this too, although we don't have any branches in this code?
Yeah. So branches make things even more complicated. You know, they make them more complicated for the hardware, and they make them more complicated for the compiler. Because, in fact, you know, having branches is one of the reasons why a compiler cannot look at a big piece of code. Usually, the compiler stops at a branch. So it's, you know, branches define the boundaries of scheduling regions. You know, usually a compiler does a basic block. We haven't introduced the concept of a basic block, but it's something that we will be introducing later. And same thing for the machine. You know, if the hardware starts to execute beyond a branch, so that's speculative execution that may get, it cannot commit it, right? The hardware cannot commit what gets executed after a conditional branch until that branch is resolved. So again, you know, the branch is an obstacle for the hardware as well. So branches complicate things, but all meaningful programs have branches, have conditional branches. Can you imagine a meaningful program without if-else? So it's not going to be very useful. Well, you have the if-else and you have the loops. The loops are also backward branches. So without conditionals and without loops, you're not going to write a meaningful program, a useful program. So a useful program makes things complicated. All right, so now we have, you know, we know what instruction scheduling is. We know what the register allocation is, and they conflict with each other. So minimizing the number of cycles conflicts with minimizing the number of registers. And this is typical for compiler optimizations to conflict with each other, to interact with each other. So some, you know, improving something can make something else worse. That's why optimizing code, you know, generating you know, good code, efficient code, is a non-trivial task. There are lots of you know, trade-offs, lots of conflicting objectives, and that's why it's a very complicated process. And you know, there is no compiler that can generate perfect code all the time. Compilers hopefully generate good code in most cases. Okay. Any question? So
Are out-of-order processors common?
Yeah. So Intel x86 is an out-of-order processor. So that's the prominent processor on desktop and laptops and workstations. So Intel x86 is out of order. Even ARM processors, the modern ARM processors, are out of order these days. Yeah. Yeah, and of course, Intel and AMD are both out of order. Okay, other questions? Okay, so basically this ends our extended overview of compilers. So what we have covered so far is the what, what compilers do and what the different parts of the compiler do. We haven't studied the how, the algorithms that are used. So, we studied the concept of instruction scheduling, but we haven't studied a specific algorithm for doing instruction scheduling. So from next lecture, we will start studying the algorithms for the different parts of the compiler. And what will be the first part that we will be studying?
Scanning.
Yeah. What's the first part in the front end? What's the first phase in the front end?
Scanning.
Scanning. Yeah. So next time we will start studying scanning, how scanning is done using finite automata and regular expressions. Okay?